Welcome to the Cosmic Frontier. Today we're exploring one of the greatest mysteries of the universe, the origin of our moon. Our moon is more than just a glowing companion. It's a planetary enigma, our moon, a familiar sight in the night sky, often taken for granted. But have you ever stopped to wonder where it came from, or how it came to be? The moon is more than just a pretty face. It's a celestial body with a story to tell. It's a celestial puzzle, a mystery that has captivated scientists for centuries, driving them to explore and understand its secrets. Unlike other moons in our solar system, our moon is surprisingly large compared to its host planet, Earth, making it a unique subject of study. It's also made of remarkably similar materials, with a few key differences that have left scientists scratching their heads and pondering its origins. The moon's orbit is another piece of the puzzle, adding to the intrigue. It's not perfectly circular, but slightly elliptical, which raises more questions. And it's tilted at an angle relative to Earth's orbit around the Sun, adding another layer of complexity. These orbital quirks suggest a dynamic and perhaps even violent past, hinting at dramatic events in the early solar system. The question of the moon's origin has long been a subject of debate and speculation among scientists and astronomers. Over the years, several theories have emerged, each attempting to explain how our celestial neighbor came to be, each with its own merits and flaws. For centuries, the prevailing view was that the moon formed alongside Earth from the same primordial cloud of gas and dust, a theory that seemed plausible at the time. However, this theory, known as the co-accretion hypothesis, struggled to explain the differences in composition between the two bodies, leading to further questions. Other early theories proposed that the moon was a wandering body captured by Earth's gravity, a scenario that also faced scrutiny, or that it spun off from a rapidly rotating early Earth, a dramatic and fascinating idea. These theories, too, face significant challenges in explaining the moon's unique characteristics, leaving scientists searching for more answers. The mystery of the moon's origin is a testament to the vastness and complexity of our universe, a puzzle that continues to intrigue and inspire. It's a reminder that even in our own cosmic backyard, there are still mysteries waiting to be solved, waiting for the curious minds to uncover. The quest to understand the moon's formation is a journey into the heart of our solar system's history, a journey filled with wonder and discovery, a journey that continues to this day, as modern astronomers and scientists delve deeper into the mysteries of our celestial companion. In the mid-1970s, a new theory emerged that would revolutionize our understanding of the moon's formation, the giant impact hypothesis. This theory posited that the moon was born from a cataclysmic collision between the early Earth and a Mars-sized protoplanet named Theia. Imagine, if you will, the early solar system, a chaotic and violent place where planets were still forming and colliding. According to the giant impact hypothesis, Theia, a rogue planet, found itself on a collision course with the young Earth. The impact was colossal, releasing an unimaginable amount of energy. The impact vaporized much of Theia and a significant portion of Earth's outer layers, blasting molten rock and debris into space. This debris, caught in Earth's gravitational pull, eventually coalesced to form the moon. The giant impact hypothesis quickly gained traction among scientists, offering a compelling explanation for several of the moon's unique characteristics. The impact scenario could explain the moon's large size relative to Earth, as well as its orbital tilt and composition. The heat generated by the impact could have vaporized lighter elements, leaving the moon depleted in volatiles compared to Earth, which was a key observation that previous theories struggled to explain. The giant impact hypothesis, while groundbreaking, was not without its flaws. As scientists delved deeper into the details of the impact scenario, they encountered inconsistencies between the model's predictions and the actual composition of the moon. These discrepancies, particularly concerning the isotopic similarities between the Earth and the Moon, cast a shadow of doubt on the theory, prompting scientists to refine and revise the impact model. While the giant impact hypothesis elegantly explained many aspects of the Moon's existence, it stumbled when it came to certain compositional details. The theory, which posits that the Moon was formed from the debris of a colossal collision between Earth and a Mars-sized body named Theia, seemed to fit well with many observations. However, it left some critical questions unanswered. One of the most significant challenges was the issue of isotopic similarities. Scientists were puzzled by the fact that the isotopic ratios of certain elements on the moon were almost identical to those on Earth. Isotopes are like atoms with different weights due to varying numbers of neutrons. These subtle differences can tell us a lot about the origins and history of celestial bodies. Measurements revealed that the Earth and the Moon have remarkably similar isotopic ratios for elements like oxygen, titanium, and tungsten. This was a surprising discovery because it suggested a closer relationship between the two bodies than previously thought. This was unexpected. The standard giant impact model predicted that the Moon should be composed primarily of material from Theia, the impactor. If Theia had a different isotopic signature than Earth, the Moon should have inherited this difference. The similarity in isotopic ratios suggested that either Theia had a composition very similar to Earth, or the mixing of materials during the impact was more thorough than the model predicted. If Theia had a different isotopic signature than Earth, the Moon should have inherited this difference. The fact that Earth and the Moon are nearly isotopic twins suggested that the impact scenario, as initially conceived, might be too simplistic. The fact that Earth and the Moon are nearly isotopic twins suggested that the impact scenario, as initially conceived, might be too simplistic. This led scientists to reconsider the details of the collision and the subsequent formation of the Moon. Another challenge was the presence of volatile elements on the Moon. These elements, which include substances like water, are typically lost during high-temperature events. Volatile elements like water have low boiling points and are easily vaporized at high temperatures. The intense heat generated by the giant impact was expected to have vaporized most, if not all, volatiles. The intense heat generated by the giant impact was expected to have vaporized most, if not all, volatiles. However, recent studies have revealed the presence of water ice in permanently shadowed craters at the lunar poles. This discovery was surprising and suggested that some volatiles had somehow survived the cataclysmic impact. This finding, along with the detection of other volatile elements in lunar samples, posed a significant challenge to the giant impact hypothesis. Scientists had to rethink how these elements could have been preserved. How could these volatile elements have survived the fiery cataclysm of the impact? This question led to new theories and models that aimed to explain the presence of these elements. These compositional conundrums highlighted the need for a more nuanced understanding of the giant impact event. It became clear that the standard model, while a good starting point, needed some adjustments to fully account for the observed characteristics of the Moon. This ongoing research continues to refine our understanding of the Moon's formation and its complex history. Alternative theories, capture and fission. Before the giant impact hypothesis took center stage, other theories attempted to explain the Moon's existence. These theories, though less popular now, played a crucial role in shaping our understanding of lunar formation. Two prominent contenders were the capture theory and the fission theory. Each of these theories offered unique perspectives and explanations for the Moon's origin. The capture theory proposed that the Moon formed elsewhere in the solar system and was later captured by Earth's gravity during a close encounter. This theory suggested a dramatic cosmic event where the Moon was pulled into Earth's orbit. This idea had a certain appeal, as it could explain the Moon's different composition compared to Earth. The distinct differences in the isotopic signatures of lunar rocks and Earth rocks seemed to support this theory. However, capturing a large body like the Moon into a stable orbit is incredibly difficult. The mechanics of such a capture would require precise conditions that are highly improbable. The capture process would likely result in a highly elliptical and unstable orbit, unlike the Moon's relatively circular path. This discrepancy posed a significant challenge to the capture theory. Additionally, the capture theory struggled to explain the Moon's large size relative to Earth. The sheer scale of the Moon made the capture scenario even more unlikely. The fission theory suggested that the early Earth was spinning so rapidly that it flung off a chunk of material that eventually became the Moon. This theory painted a picture of a young, dynamic Earth. This idea was supported by the fact that the Moon's composition is somewhat similar to Earth's mantle. The similarities in the chemical makeup provided some evidence for this theory. However, the fission theory faced significant challenges in explaining the Moon's angular momentum, which is a measure of its rotation and orbit. The dynamics of such a process were difficult to reconcile with observed data. For the Earth to spin off the Moon, it would have needed an implausibly high initial rotation rate. Such a rapid spin was not supported by geological evidence. Furthermore, the fission theory couldn't adequately explain the differences in volatile elements between Earth and the Moon. These differences suggested a more complex formation process. While these alternative theories offered intriguing possibilities, they ultimately fell short in explaining the full range of the Moon's characteristics. The search for a comprehensive theory continued. The giant impact hypothesis, despite its challenges, remained the most plausible explanation for the Moon's origin. It provided a coherent narrative that matched much of the available evidence. However, it was clear that the impact scenario needed further refinement to address the compositional discrepancies that continued to puzzle scientists. The quest to fully understand the Moon's origin was far from over. Upgraded impact models fine-tuning the collision. The challenges posed by isotopic similarities and the presence of volatiles on the Moon didn't invalidate the giant impact hypothesis. Instead, they spurred scientists to develop more sophisticated and nuanced models of the impact event. One such model, proposed by Dr. Robin Canup and her colleagues, suggested that the impact between Theia and Earth was even more energetic than initially thought. This high-energy impact would have created a vast, hot, and rapidly rotating cloud of vaporized rock and debris known as a synestia. Within this synestia, material from Earth and Theia would have thoroughly mixed, explaining the isotopic similarities between the two bodies. Another key refinement involved the concept of evection resonance. Evection resonance describes a gravitational interaction between the Earth, the Moon, and the Sun that can affect the Moon's orbit over long periods. This resonance could have acted as a brake on the early Moon, gradually circularizing its orbit and pushing it farther away from Earth. This revised model, incorporating a more energetic impact and the effects of evection resonance, addressed some of the shortcomings of the standard giant impact hypothesis. It offered a more complete picture of how the Moon might have evolved into the celestial neighbor we know today. The updated model provided a more plausible explanation for the Moon's current orbit and its isotopic similarities with Earth. However, the question of how volatiles like water survived the impact remained a topic of ongoing research and debate. Explore the mysteries of the cosmos with us. Subscribe now.